Okay, here are your notes on section 4.3. We're looking at basically taking 4.1 and adding it to 4.2. So relating gravitational field strength to gravitational force. And so, yeah, in section 4.2, which you just finished, we are looking at this formula. Okay, so our gravitational or force due to gravity is equal to the universal gravitational constant times the mass of the test times the mass of the source divided by r squared. So like in this case here, if we're looking at the force due to gravity on the moon, okay, mass of the test would be the mass of the moon, mass of the source would be the mass of Earth, okay, and then r would be the distance from the center of the Earth to the center of the moon. Okay, in the first, like section 4.1, we looked at force due to gravity is equal to mass of the test times g, or like acceleration due to gravity, or gravitational field strength is another way to say that. Okay, and so because Fg is equal to mass of test times gravitational field strength, we can replace Fg with this. So that's what we did in this formula here. Okay, the mass of our test times gravitational field strength is equal to universal gravitational constant times the mass of test times mass of the source divided by r squared. Okay, because like when we're canceling things out, we divide both sides by the mass of the test, which then gets rid of that. So really, to find the gravitational field strength of something, we just need the universal gravitational constant times the mass of the source divided by r squared. So like if we want to find out what is the gravitational field strength on the Earth, we just need to know the mass of the Earth and the radius of the Earth where that person is standing to then find out what g is, lowercase g. So we use this formula to calculate gravitational field strength when we're given information about the source of the field. So we have to know what the mass of the source of our field is. Okay, again, lowercase g is our gravitational field strength. It is measured in newtons per kilogram. Okay, for this, because we're like, it's also equal to acceleration due to gravity, which would be in meters per second squared. But for this part of this unit, okay, we're going to focus on the gravitational field strength, so we'll put those measurements in newtons per kilogram. Okay, again, capital G, and that's it's important to have lowercase g and capital G. They're two different numbers, so make sure you keep them different. Okay, lowercase or capital G is the universal gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Again, that number is found on your formula sheet. And then mass of source is the mass of the source of the field in kilograms. Okay, a lot of them, we're going to be talking about planets and like celestial things. Okay, the ones that you need are all on your formula sheet. Okay, the masses. And then the radius, distance from center of the object generating the field, and that's measured in meters. Okay, so be careful of that. Sometimes you'll be given in kilometers, and make sure you do that conversion. Okay, so yeah, here's some different ones that you'll have to kind of find. And so different masses, these are all the ones that you need are on your formula sheet. Okay, make sure like mass, and these are the equatorial, so like at the okay, at the equator of each of these, so halfway across, okay, that's the radius, which actually, and the radius will change depending on where you're standing on that celestial body. Okay, so example, okay, is comparing the gravitational field strength on the Earth compared to gravitational field strength on the moon. Okay, and so the capital G doesn't change, 6.67 times 10 to the negative 11. Okay, for the mass of the Earth, you'd pull that off of this, so 5.97 times 10 to 24. Okay, and then radius of the Earth squared, put those numbers in. Okay, and in this example here, so this is out of your textbook, you're looking for like the final answer is how much more is the gravitational field strength than on Earth compared to the moon. And so then once you found your gravitational field strength on the moon, you can compare the two by dividing them, and you find that the gravitational field strength on Earth is 6 times more. Okay, another example out of your textbook. Okay, it could be asking for, like in this case, it's asking for the force due to gravity. This is on page, page 220 of your textbook. It goes through it. Okay, but basically, you want to find, for like this question, to find the force due to gravity and comparing them, you have to find the gravitational field strength to start with, because Fg is equal to m times g. So to start with, you have to use your original formula, like the gravitational field strength of each, just like we did in the last question. Once you have that, then you can times it by the mass of the person that's standing on it to find out what the actual force due to gravity that's acting on the person. Okay, the different values of gravitational field strength on Earth. Okay, so basically at the equator, our Earth is kind of slightly bigger at the equator, the radius. Okay, and so as you get further away from the equator, closer to the poles, okay, the field strength goes up because the radius would then be getting smaller. Okay, and then also with that, like if the radius gets smaller, your gravitational field strength will increase. The mass doesn't change in the gravitational, so really it's just looking at the radius. And true versus apparent weight. So this is kind of looking at your weight. So again, weight is equal to Fg. Okay, so the true weight of something is a gravitational force acting on the object. So to find your true weight, you would take your mass, okay, times it by the 9.81, okay, to find your true weight. Okay, and so like it's kind of with these examples, when we're looking at like apparent weight, if someone's just at rest, okay, or not moving, okay, or moving at a constant velocity, okay, again with no acceleration, then our force due to gravity is equal and opposite to our normal force. Okay, and so that's usually what's happening. So this person's at an elevator at rest. And most of these, like when we're talking about apparent weight, there has to be a reason the person's moving up or down. So a lot of these questions have to do with an elevator or on an airplane or something like that. Okay, and so yeah, because this person, even though like an elevator's at rest, or if the elevator's moving at constant velocity, okay, if we have no acceleration, we have a constant velocity, that's when our true weight and apparent weight will be equal. And like basically our true weight is Fg, and then the force, normal force, would be equal and opposite. Okay, the forces are balanced. Okay, if the elevator is accelerating up, okay, we're gonna, like if we're standing on a scale in that elevator, when that elevator first starts moving up, okay, we're pushing that scale down. You can see that here. Like if our normal force due to gravity is 600, this is at about 750. Okay, meaning that our normal force is greater than our force due to gravity, and you can see that here in the free body diagram. Okay, the vector for our normal force is a lot longer because of the acceleration going up. Okay, so we have an unbalance in force, okay, and that's going to change like our apparent weight. So in this case, like the apparent weight, okay, is going to be 750 newtons. Okay, if an elevator is accelerating down, it's going to be the opposite. You're going to seem a little bit lighter. Okay, and that's what you can see here. It's about 525, okay, compared to the original 600. So again, we'll have now our force due to gravity is greater than our normal force. Okay, that's pushing us up. Okay, which we can see there. Okay, and so the apparent weight, to find the apparent weight of any person, okay, is the negative of the normal force acting on the object. So you just need to find the normal force. Okay? And so like in these, again, you'll have acceleration up or down. So in most cases, the person will be on an elevator, or like some sort of airplane that can go up or down, or a helicopter, okay, where it changes your normal force depending on whether you're accelerating up or accelerating down. Okay, there's another example of this, okay, in your textbook on page 224. Basically, it's looking at an astronaut in a spaceship is standing on a scale in a rocket. The acceleration of the rocket is going up. Okay, calculate the true weight and apparent weight during this liftoff. So again, lots of the force of the rocket is going up, and so the person's pushing down on the floor, so their normal force is going to be a lot higher. And so you just have to find the normal force. And so again, Fg is equal to the mass times gravity, so we can always find that. F net, for given an acceleration, we can find F net, and then F net's always going to be your normal force plus your gravitational force. In this case, gravity is going in opposite direction of F net. And so you can find your normal force, okay, by using these two calculations, and then the apparent weight will be equal to the negative normal force. And so that's kind of the steps in solving it. Again, that example is on page 224 of your textbook. Okay, another example, with apparent weight, okay, is free falling. The only force, if someone's in free fall, that's acting on that mass is the acceleration due to gravity, or the force due to gravity. Okay, and so we have no normal force. There's nothing pushing up, okay, that's balancing out that force. So just the full force is going down. Okay, and so the apparent weight in this case of someone in free fall is 0 newtons. Okay, and so that's kind of, like in free fall, and we'll talk about like how that affects astronauts and so on. So weightlessness, a satellite is able to orbit because of the shape of the Earth. Okay, and so it basically, and we'll talk about this more in the next unit when we talk about centripetal motion, but this, because of the shape of the Earth, it curves away from the satellite. So the satellite's almost in constant free fall around the Earth. Okay, so when you consider like a satellite like the International Space Station, the reason why the astronauts in that space station or in any orbit, okay, feel weightless is not because of due to the lack of gravity. They aren't that far away from Earth that gravity has no effect on them. Okay, really what's happening in that capsule, or like in the International Space Station, is everything in it is in free fall. So like if you they have different airplanes and stuff you can go on now and kind of feel this weightlessness, and basically what it does is the airplane falls and you can be in free fall for a little while and it feels like you're in a weightless environment. Okay, but really gravity is still acting on you, but you're just going down at the same rate as the plane, and so you're in free fall together. All right, so for this section, there's lots of examples in the textbook on how to do stuff. Always, you can refer to that. I'll post some extra videos to kind of help you along with it. Okay, and we have different examples, and then you can go through the assignment 4.3 and you'll have a quiz probably early next week.